how can measurements of time and space depend on motion and gravity while the laws of physics remain objective?
Well, I think that's really the absolute core of the issue here. There is this pervasive cultural misconception where people just kind of shrug and say, well, everything is relative.
Right.
And they use it to imply that physical facts are just matters of opinion or that reality depends purely on your personal perspective. But relativity makes the exact opposite claim.
Oh, wait, really?
Yeah, it states that while different observers might indeed record completely different numbers for, say, a distance or a duration, those observers remain tightly connected by precise mathematical transformation laws.
Okay.
There are invariant physical relationships underneath it all. I mean, the universe is entirely objective. It's just that tools for measuring it are relative to our state of motion.
Which completely upends standard human intuition.
Oh, absolutely.
So we are going to explore how relativity fundamentally changes how we measure durations, distances, simultaneity, and gravitational motion. And to really unpack this, our roadmap for this deep dive is going to move pretty systematically. We'll start with the basics, rods, clocks, events, and inertial frames. And from there, we'll get into the invariant speed of light, the relativity of simultaneity, time dilation, length contraction, and space-time intervals.
Right.
Then we'll dive into energy and momentum, the equivalence principle, and how all that leads to curved space-time.
Yeah.
And finally, we'll unpack the big phenomena. So gravitational time dilation, light bending, frame dragging, gravitational waves, black holes, and then wrap up with Einstein's later unification attempt.
It's quite a journey. And the foundational text for this entire progression is Albert Einstein's canonical book, The Meaning of Relativity.
Right.
To give you a bit of context, this work developed directly from a series of lectures he delivered at Princeton University back in, I think it was May 1921.
Yeah, that sounds right.
And what makes this book so vital is that it represents a mathematically serious synthesis of both his special and general theories of relativity. I mean, it bridges that gap between abstract coordinate geometry and actual measurable physical reality.
Exactly. And the mission of this deep dive is to explore the physical procedures behind the theory. Because before we can even touch the abstraction of curved space-time or, black holes, we have to talk about what it actually means to measure something. Historically, going all the way back to Newton, people treated space and time as these invisible, rigid containers.
Right, like a stage.
Exactly. Space was a fixed theater stage, and time was this universal ticking clock in the background that everyone shared. But if we want to map reality, we can't measure an invisible container.
No, you can't.
If I want to measure the length of a table, I use a physical rod, like a ruler. If I want to measure duration, I use a physical clock. And if I want to map what physicists call events, which is just a specific location at a specific moment, I use light signals.
Right. And that is where the whole framework really starts, the observer and the measurement procedure. By operationalizing length and time through reproducible physical procedures, like actually laying down rulers end to end or counting the ticks of a physical watch, we completely remove that old assumption of absolute space.
Okay, I see.
And to go back to our central tension, this operational definition does not mean reality is subjective.
Right.
It just means that physics requires rigorous metrology. If an observer standing on a station platform and an observer riding on a moving train are going to compare notes about an event, they can't just assume their clocks are perfectly in sync.
Oh, because they're moving differently.
Exactly.
Wow.
They must first define exactly how they are synchronizing their clocks and how they are laying down their measuring rods.
Okay, let's play with that train example because I think it's probably the best way to visualize this.
Here.
Imagine a train car moving perfectly smoothly along a track at a constant velocity. You pull the blinds down so you can't see outside at all. This is what we call an inertial frame. If you are inside that train car and you bounce a tennis ball on the floor or you pour a cup of coffee or even set up some high-tech laser experiment, the physics looks exactly the same as it does for the guy standing still on the station platform.
Right.
No internal experiment you run inside that closed train car can reveal your absolute uniform motion. Without looking out the window, you literally cannot prove whether you are the one moving or if the Earth is moving beneath you.
And identifying the limiting case here is crucial. Newtonian mechanics assumes you can just easily transform between these frames moving at a constant relative velocity. And to be fair, I mean, it remains an excellent approximation in our daily lives.
Sure, yeah.
When speeds are low relative to the speed of light and when gravity is weak, classical mechanics recovers the old physics seamlessly. You don't need relativity to build a bridge or throw a baseball.
Right, right.
The principle of relativity, the idea that the laws of physics take the same form in all inertial frames, has been supported to incredibly high precision. The monumental shift in our understanding really only happens when we combine this perfectly reasonable principle with something that classical mechanics just totally failed to anticipate.
Which brings us to the invariant speed of light,
Mm.
famously denoted by the letter c. So here's the setup. If no inertial frame is special, and the laws of electromagnetism are universal, then the speed of light in a vacuum must be the exact same for everyone.
Exactly.
It does not matter if the flashlight is stationary or strapped to the front of a rocket ship, the light comes out at the same speed. But this forces a massive paradox.
It does.
Let's go back to our train. Imagine an observer standing exactly in the middle of a moving train car, and another observer is standing on the station platform. At the exact fraction of a second, the train observer passes the platform observer. Lightning strikes the front of the train and the back of the train.
Okay, let's walk through this carefully.
Right. To the platform observer, the light from both the front lightning strike and the back lightning strike reaches their eyes at the exact same time. They get out their notepad, they map it out, and they say, well, those two lightning strikes happened at the exact same moment. They were simultaneous. But what about the person inside the moving train?
Right, so we have to identify the observer's frame and the invariant quantity here.
Okay.
The invariant quantity is the vacuum speed of light. Because the train is moving forward, the observer inside the train is moving toward the light waves expanding from the front strike and moving away from the light wave expanding from the back strike.
Oh, I see.
Now, since the speed of light is strictly constant for both observers, I mean, it doesn't speed up or slow down just because the train is moving. The light from the front strike literally has less distance to cover to reach the train observer.
Wow. Okay.
So it must hit the train observer before the light from the back strike. The train observer will map this out, run the calculations, and objectively conclude, well, the front strike happened first. They were not simultaneous.
So two events, like lightning strikes, separated by distance, that are simultaneous in one frame of reference, are completely sequential in another frame of reference.
Yes.
And I think the natural human instinct here is to assume someone just made a mistake. Like, there has to be a true universal background time, and one of these observers just didn't account for a delayed signal properly.
That is easily the most common misconception. It is vital to understand that neither observer has a faulty clock.
Okay.
Neither observer is being fooled by an optical illusion or some processing delay in their brain. Both have entirely valid, mathematically rigorous coordinate assignments.
That's wild.
Synchronization intrinsically depends on signal propagation and your choice of reference frame. Because the speed of light is invariant, simultaneity itself must be relative. There is no master clock for the universe.
But if some simultaneity is broken, then the way we measure duration and length has to be broken too, right?
Exactly.
This leads us directly to time dilation. If a clock moves rapidly past me, I'm going to measure its ticking as slower compared to my own stationary clock on my wrist. And length contraction? If a meter stick flies past me at a fraction of the speed of light, I will measure it as physically shorter along its direction of motion.
Yes, that's exactly right.
But help me unpack the how here. The physical reasoning is that measuring the length of a moving object requires me to note where its front end and back end are at the exact same time. If I don't mark them at the same time, I'm measuring a blur. But we just established with lightning strikes that my same time is completely different from the moving object's same time.
Right.
But still, how can reality contort this way without breaking the physical objects themselves? Like, if I see a clock ticking slower, is it jammed? If I see a ship compressed, is the metal buckling?
It is essential to correct two major misconceptions right here. First, moving clocks are not mechanically damaged. The slowdown is not caused by air resistance, or gears grinding together, or atoms struggling to move at high speeds. Time dilation is a fundamental property of the space-time path the clock takes.
Wow.
And second, length contraction is not a universal physical crushing force. The moving meter stick does not experience structural compression in its own rest frame.
So it's not being squished.
No, not at all. If you were riding along in a spaceship with that meter stick, you would measure it as exactly 1 meter long. You would feel no crushing pressure. In fact, looking out your window, you would see the rest of the universe contracted.
Wait, really?
Yeah, it is purely a consequence of how measurements of space and time are made across different frames of reference.
This is where we have to transition from these relative measurements to what everyone actually agrees on, because otherwise it just sounds like complete chaos.
It does, yeah.
I like to use the analogy of a loaf of bread. If I slice a loaf of bread straight down, I get a piece with a specific height and a specific width. If you take that exact same loaf of bread and slice it at an extreme angle, your slice has a totally different height and a different width.
Mm-hmm.
We completely disagree on the spatial dimensions of our slices, but we are cutting the exact same loaf of bread. In relativity, space and time are merged into a single four-dimensional structure called spacetime. Different observers, because of their different speeds, are just slicing that spacetime at different angles.
That is an excellent analogy. The loaf of bread itself is the invariant quantity, which in this mathematical framework is called the space-time interval.
Okay?
Well, you and I will assign entirely different temporal and spatial coordinates to a pair of events based on our relative motion, just like your different bread slices. If we plug our differing numbers into the metric equations of special relativity, we will calculate the exact same underlying space-time interval.
So even if we disagree on the time and the distance, the math balances out perfectly to a single agreed-upon number.
Precisely. We also all agree on what is called proper time. Proper time is the actual physical time accumulated by a specific clock moving along a specific path between two events.
I see.
So observers assign different coordinate labels, yes, but they completely agree on the invariants and the experimentally testable outcomes. The underlying reality is completely objective.
That concept of invariance, finding the thing everyone agrees on, carries over to mass and energy, too. Everyone knows Einstein's famous equation, E equals mc squared, which relates energy to mass.
Right.
As an object moves faster and faster, its kinetic energy increases. Because energy and mass are deeply connected, you read a lot of older textbooks that tell you a moving object literally gets heavier.
Oh, yes.
They claim that its mass increases with speed, which is why it gets harder and harder to accelerate it to the speed of light.
I am glad you brought that up because that is an outdated and deeply inaccurate suggestion that we must strongly avoid. It confuses the physics.
Oh, so it doesn't get heavier.
No, it is much clearer and mathematically correct to say that an object's total energy and momentum increase with velocity. The invariant physical property here is the object's rest mass.
Rest mass.
Yes, which is the mass measured in a frame where the object is totally stationary. Total energy and momentum depend entirely on the observer's frame, but the rest mass remains an objective invariant quantity agreed upon by everyone.
Okay, that makes sense.
And this isn't just theory. I mean, this invariant rest mass is verified daily in modern particle colliders, where kinematics strictly rely on this fact.
Okay, so that essentially establishes the metrology of special relativity. We're dealing with flat space-time, constant velocities, trains moving in straight lines. But the universe is messy.
Very.
It has gravity. Things accelerate. To bridge the gap from acceleration to gravity, we construct another thought experiment. Imagine a person inside a sealed elevator car with no windows. First, let's put that elevator out in deep space, far away from any planets or stars. We attach a rocket to the bottom of the elevator that accelerates it upward at 9.8 meters per second squared. Right? The person inside feels their feet pressed firmly to the floor. If they hold out an apple and drop it, the floor accelerates up to meet the apple, so from their perspective, the apple accelerates to the floor at 9.8 meters per second squared.
Right. Now, place that exact same sealed elevator car just sitting stationary on the surface of the Earth.
Okay.
The person inside feels the exact same weight pressing them to the floor. And if they drop the apple, it falls to the floor in the exact same way. Without looking outside, they cannot tell if they are being accelerated by a rocket in deep space or sitting in a gravitational field.
And it works in reverse, too. If the elevator is in deep space with the rocket turned off, the person floats. They are weightless. If we put the elevator in Earth's gravitational field, but cut the cable so it plummets down a completely frictionless elevator shaft, the person inside also floats. The apple hovers right next to them in midair.
Yeah.
This is the equivalence principle. Local freefall removes uniform gravitational effects entirely.
We must identify the limiting case here, though. The equivalence is strictly local. It only works in a small area.
What do you mean?
Well, imagine if your elevator was the size of the Earth and you dropped two apples at completely opposite ends of the car. They wouldn't fall perfectly parallel to each other. They would both fall toward the Earth's center of mass.
Oh.
So over extended regions, their paths would slightly converge.
Ah, so they would slowly drift toward each other as they fell.
Exactly. That convergence is tidal gravity, and it remains detectable. You can't just define that away. But by recognizing that free-falling motion locally removes uniform gravitation, Einstein had an absolute breakthrough.
Right.
He linked gravity not to an invisible force pulling objects through a static space, but to the geometry of the space itself.
This is the leap into curved spacetime. Gravity is not an ordinary force acting within a fixed, grid-like Euclidean space. Instead, matter and energy physically warp the four-dimensional spacetime around them. And objects simply follow the straightest possible paths through that curved environment. Now, the cultural shorthand for this, the metaphor everyone learns in high school, is the rubber sheet analogy.
Oh, boy.
You imagine a bowling ball sitting on a trampoline, warping the fabric down, and then you roll a marble around it, and the marble orbits the bowling ball because of the dip in the sheet.
And I need to make it extremely clear that the popular rubber sheet analogy is highly limited and, honestly, quite flawed.
Really. It's basically the only way most of us visualize it. Why does it fail?
Think about it. The analogy relies on an external force to work. It requires Earth's actual gravity pulling the bowling ball down to stretch the rubber sheet, which is supposed to be explaining gravity in the first place.
Oh, wow. Yeah, that is circular reasoning.
It is. But more importantly, it almost entirely obscures the critical role of the time dimension. Space-time curvature is not just bent space. It is deeply about bent time. A better analogy would be to look at the longitude lines on a globe. At the equator, those lines are perfectly parallel. But as you follow them north, they naturally converge and cross at the North Pole.
Because the surface of the globe itself is curved.
Precisely. No invisible force pulled those lines together. The geometry of the space simply dictated their path. In relativity, we introduce the metric as the mathematical measurement procedure that maps out these complex spacetime intervals.
Right.
When an object is in free fall, moving without rockets or physical forces applied to it, it traces a path called a geodesic. Geodesics are just locally unforced motions through this curved four-dimensional geometry.
Just like tracing a straight line on a curved globe.
Yeah.
Okay, so because time itself is part of this curvature, we get gravitational time dilation. Let's construct this physically so we can visualize it.
Sure.
Imagine we have two highly precise clocks. We leave one in a deep valley, close to the center of the Earth, deeper in the gravitational potential well. We take the other clock, hike up, and leave it at the peak of a high mountain. The clock in the valley where gravity is stronger actually accumulates less proper time. It physically ticks slower relative to the clock sitting up on the mountain.
And we can see this effect even more clearly if we send signals between them.
Right. If the valley clock sends a laser signal up to the mountain clock, the light literally has to climb out of the gravity well.
Exactly.
As it climbs, it expends energy. But light can't slow down. The speed of light is constant, as we established. So if it loses energy but can't lose speed, how does it pay the toll? Its frequency drops.
Yes.
The light waves get stretched out. It shifts toward the red end of the spectrum, which we call gravitational redshift. We also face a signal delay as it propagates near the massive body of the Earth.
We can confidently categorize this as observed evidence. This is not just theoretical math on a chalkboard. Modern optical atomic clocks are incredibly sensitive. I mean, it's so sensitive, in fact, that they can detect this gravitational redshift over height differences of just a few millimeters in a laboratory.
Wow, just millimeters.
Yes. And this isn't just trivia. It connects directly to satellite navigation.
Oh, like the GPS in our phones.
Exactly. The global positioning system relies on a network of satellites orbiting high above the Earth. Now, they're moving very fast, which means special relativity says their clocks should tick slower compared to ours on the ground.
Right, because of the speed.
But they are also sitting high up in a much weaker gravitational field, which means general relativity says their clocks should tick faster compared to ours on the ground.
Wow, so the two effects are fighting each other.
They are. The precise timing required for GPS inherently relies on calculating both the special relativistic time dilation from their speed and the general relativistic time dilation from their altitude. Without these constant metric calculations correcting the clocks, the GPS network would fail by miles within a single day.
That is incredible. So moving from the Earth out into the wider solar system, We can observe how massive distributions of matter deflect light. If a star is sitting far behind the sun, the light from that star passes through the curved spacetime around the sun, and its path is bent.
Hmm.
When that light reaches our telescopes, we see the star in a slightly different position than it actually is. We also see this curvature affect planetary orbits. Mercury's orbit features this anomalous precession. It doesn't trace a perfect closed ellipse. It traces out a rosette pattern over time that Newtonian mechanics could never fully account for.
I want to clarify something here for the listeners. When we talk about Mercury's orbit, you might hear the term solar system ephemerides.
Wait, what's an ephemeris? Are we just talking about planetary tracking maps?
Essentially, yes. An ephemeris is a highly precise mathematical model or table that tracks the positions of astronomical objects over time. These phenomena fall strictly under established theory and observed evidence.
Okay.
The modern solar system ephemerides map Mercury's weak field orbital precession flawlessly using Einstein's equations. Furthermore, gravitational lenses in astronomy show us massive galaxies bending the light of background quasars, magnifying them, and sometimes multiplying their images into arcs and rings.
And if a mass is not just sitting there, but rotating, like the Earth spinning on its axis, it actually drags the fabric of space-time around with it. This is called frame dragging.
Yes, and this was experimentally measured by the NASA Gravity Probe B satellite, which tracked the incredibly subtle geodetic and frame-dragging drifts of ultra-precise gyroscopes in Earth orbit.
Wow.
But we must correct a lingering misconception regarding frame dragging. It does not imply spacetime is a literal material fluid swirling around the Earth like water in a drain. There is no friction dragging things along.
Oh, I see.
It simply means the local inertial frames, those geodesics we talked about, the straightest possible paths, are geometrically twisted by the rotating mass.
Let's scale this up. Let's look at the extremes. Strong field gravity. In electromagnetism, if you accelerate an electric charge, it produces electromagnetic waves like radio waves.
Right.
So logically, if you accelerate an asymmetric mass distribution, it should launch ripples in the metric of spacetime itself. Imagine two massive compact objects like dead neutron stars or black holes orbiting each other tightly. As they spiral inward, moving at massive fractions of the speed of light, they disturb the spacetime geometry. They radiate energy outward in the form of gravitational waves. As these waves pass through the Earth, they literally stretch and squeeze the distances between objects.
And this is now observed evidence, primarily driven by the LEGO, Virgo, and KGRA collaborations. The measurement procedure here utilizes massive laser interferometers.
Right.
By firing lasers down perpendicular vacuum tubes that are several kilometers long, physicists can measure the fractional stretching and squeezing of spacetime to an astonishing degree of precision. I mean, we are talking fractions of the width of a proton.
Which is just mind-blowing.
It really is. The signals show characteristic in spiral, merger, and ring-down patterns that match the relativistic theory perfectly. The necessary misconception to correct here, however, is that gravitational waves are somehow sound waves.
Oh yeah, you hear that a lot.
You will often hear people say, we can hear the universe because scientists convert the wave data into audio files for us to listen to. But gravitational waves are not sound, and they do not require a material medium like air or water to travel through. They are self-propagating ripples in the measurement of space-time itself.
The ultimate extreme of this geometry, of course, is a black hole. If a really massive star exhausts its nuclear fuel and undergoes a catastrophic gravitational collapse, the density of matter becomes so extreme that it severely warps spacetime.
Yes.
It builds a causal boundary around itself called an event horizon. Any light emitted from inside that boundary is bent so severely by the sheer curvature of spacetime that all possible paths simply point inward. Outward light cannot reach distant observers.
Black holes are also solidly observed evidence today. Through horizon-scale imaging, like the famous pictures of M87 and Sagittarius A star, as well as observing stellar orbits at the galactic center and detecting binary mergers, the existence of black holes is firmly validated. But we must correct two major pervasive misconceptions. First, an event horizon is not a solid physical surface. It is purely a mathematical boundary of causality.
Oh, so you wouldn't crash into it?
No, if you were falling through one, assuming for a moment you survived the horrific tidal forces tearing you apart, you would not hit a wall. You would just cross an invisible threshold.
And the second misconception?
That black holes suck everything in like cosmic vacuum cleaners. They do not. If we somehow magically replaced our sun right now with a black hole of the exact same mass, the Earth would not be sucked in.
Wait, really? We'd just stay where we are?
We would go dark, and we would freeze, but gravitationally, the Earth would continue along its exact current orbital geodesic. The distant orbital dynamics are just ordinary gravity.
Wow.
It is also important to note that inside the black hole, at the central singularity, the point of infinite density at the core, that marks the strict limit where this classical theory of relativity completely breaks down.
Scaling up from a single black hole, we can expand our view to the entire universe. General relativity provides the fundamental framework for cosmology and global geometry. The equations allow for a dynamic, changing universe, linking the redshift of distant galaxies, the cosmic distance scale, and the entire history of cosmic expansion.
Expanding universes are established theory, heavily supported by observations of the cosmic microwave background and large-scale structure mapping. However, it is historically necessary to point out that Einstein's original motivation actually included a static universe model.
Oh, you wanted it to be still.
He didn't initially like the idea of a dynamic universe, so he famously introduced a cosmological constant to his equations to artificially keep the universe still and stable.
I see.
That specific static model is categorized today purely as a historical proposal. The expanding relativistic cosmology is the robust modern framework we use.
In his later years, Einstein spent immense effort attempting to mathematically unify gravitation and electromagnetism into a single, elegant framework. He wanted one set of equations to explain everything. The later editions of The Meaning of Relativity actually explore his non-symmetric unified field work.
And we must be clear that this is also a historical proposal. Einstein's non-symmetric unified fieldwork is historically important as a record of a major research ambition from one of history's greatest minds, but it was strictly unsuccessful.
Okay, so it didn't pan out.
No, it is not the accepted modern framework, and it is entirely distinct from the standard model of particle physics, which successfully unites electromagnetism with the nuclear forces.
Which leaves us at the current frontier of physics.
Yeah.
General relativity is incredibly successful at mapping the macro universe. It handles everything from the GPS satellites orbiting Earth to the violent mergers of black holes billions of light years away. But when we drill down to the absolute quantum scale, when we look at the singularity inside a black hole or try to understand the earliest fraction of a second of the Big Bang, the math just stops making sense. It breaks down.
We must define the boundaries of our knowledge. General relativity is a classical theory. It does not explain quantum mechanics. A completed, unified quantum theory of gravity remains an open problem in physics.
Right.
The observational evidence supports a phenomenally precise mathematical framework for classical spacetime, but strong empirical success at the macro level does not make the theory complete at quantum scales.
So to synthesize this deep dive, relativity absolutely does not mean everything is subjective. It replaces the classical Newtonian ideas of an absolute invisible space and a universal ticking background clock with measurable operational space-time relationships.
Yes.
It recognizes, as the physicist John Archibald Wheeler once elegantly put it, that matter tells space-time how to curve, and curved space-time tells matter how to move.
Precisely. The theory ultimately preserves the objectivity of the universe. Yes, observers will assign varying coordinates to events based on their relative motion or their position in a gravity well, but those observers are bound by strict mathematical transformation laws.
Okay.
When they run the math, they will always agree on the underlying spacetime intervals, they will agree on the rest masses, and they will agree on the invariant physical rules governing reality. The universe remains a shared, objective reality.
This is an independent COSMORA HQ book overview, not an official or complete audiobook.
We encourage you to seek lawful access to the published work for the full mathematical treatment.
If this overview helps clarify these concepts for you, please subscribe, comment, and share this deep dive.
Which prediction of relativity most clearly changed your understanding of space, time, or gravity?